Hello everyone, this is our second lecture for Chapter 3 on the normal curve and normal distributions. In this lecture video, we will introduce z-scores. The standard deviation controls the spread of a normal curve. Changing the mean without changing the standard deviation moves the curve along the horizontal axis without changing its shape. The larger the standard deviation, the larger the spread of the normal curve. The area under the normal curve represents the proportion of the population with a given score, or the probability that a randomly selected individual from the population will have a given score. The question now becomes, how do I find the area under the normal curve? Finding the area under a curve requires techniques introduced in calculus, specifically the probability density function, which are beyond the scope of this class. An alternative would be to use a series of tables to find areas. However, this would result in an infinite number of tables being created for each possible mean and standard deviation. A solution to the problem is the z-score. The z-score identifies position and potential outliers as well. Remember, the empirical rule tells us that for a bell-shaped distribution, it is unusual for a data value to fall more than 3 standard deviations from the mean. Z-scores are based on raw scores, means, and standard deviations. There are 3 things that z-scores can do for us. 1. Identify and describe the exact location of every score in the distribution in standard deviation units. 2. Standardize an entire distribution so that we can determine probabilities. And 3. Take different distributions and standardize them, making them equivalent so that we can compare different distributions. An example would be admissions and records personnel who have to determine which students get acceptance letters. Some students take the ACT exam and others take the SAT exam. These exams are standardized, and A&R folks can now compare students based on their standardized scores, so we can compare apples to oranges using z-scores. The z-score for a data value measures how far specific data values are from the mean in standard deviation units. A z-score tells us how many standard deviations a score is away from the mean and in which direction. There are 2 components to z-scores. First, the sign. If a z-score is positive, then we know that the score is above the mean. If a z-score is negative, then we know that the score is below the mean. The second component is the magnitude of the z-score. This tells us how far away from the mean the score falls in standard deviation units. Remember, a data value that falls more than 2 standard deviations from the mean is a potential outlier in the behavior sciences. Here is an example of how we would compare 2 different exam score distributions. For both distributions, notice mu is equal to 70. But for one distribution, sigma, population standard deviation, is equal to 3, and for the other, sigma, or population standard deviation, is equal to 12. Notice how different a score of 76 is for the 2 distributions. In the first distribution, an exam score of 76 is much further away from its mean of 70, whereas in the second distribution, the same score of 76 is much closer to its mean. A z-score is calculated by subtracting the mean from the data value and dividing by the standard deviation. This tells you the number of standard deviations that score is away from the mean. The distance from the mean expressed in standard deviations is the z-score associated with that raw score. The steps to calculate a z-score, or to change a raw data value or score to a z-score, are as follows. So 1, calculate the deviation score. Subtract the mean from the data value. X minus mu for population, or X minus M for sample data. Step 2, calculate the z-score by dividing the deviation score by the standard deviation. Sigma for population, or S for sample data. So the z-score formula for population is z equal to x minus mu divided by sigma, and the z-score formula for sample is it's z equal to x minus m divided by s. Okay, let's take the pulse rate distribution from our empirical rule example in the previous video. Remember, pulse rates had a mean of 72 and a standard deviation of 6. In this distribution, a raw score of 82 would have a z-score of 1.67. Calculated as 82 minus 72 divided by 6, which gives us 10 divided by 6 equal to 1.67. The interpretation is as follows. The pulse rate of 82 is exactly 1.67 standard deviations above the mean. We say above the mean because this is a positive z-score. The score is above the mean. We could also find a raw data score if we know its z-score. Using a little algebra, we take the z-score formula and turn it into x is equal to mu plus z times sigma, or x is equal to m plus z times s. Now, using the previous example, we want to find the pulse rate for a z-score of 2.5. Remember, pulse rates had a mean of 72 and a standard deviation of 6. So the raw score, x, is equal to 72 plus 2.5 times 6, which equals 72 plus 15, which is equal to 87. So the interpretation here is a z-score of 2.5 corresponds to a pulse rate of 87. The z-score distribution is also called the standard normal distribution. The z-score distribution always has a mean equal to 0 and a standard deviation equal to 1. Remember the empirical rule? The empirical rule states that approximately 68% of the data will fall within one standard deviation of the mean plus or minus sigma. Approximately 95% of the data will fall within 2 standard deviations of the mean plus or minus 2 sigma, and approximately 99.7% of the data will fall within 3 standard deviations of the mean plus or minus 3 sigma. So how is the empirical rule related to z-scores? Well, approximately 68% of the data will have z-scores between -1 and +1. Approximately 95% of the data will have z-scores between -2 and +2. And approximately 99.7% of the data will have z-scores between -3 and +3. Here is a graphical representation of z-scores and the empirical rule. This concludes our discussion for Chapter 3. The next chapter, Chapter 4, introduces the concept of probability and how it relates to z-scores.